And it is my pleasure to introduce as our first speaker our very own Chani Nava. So Chani is a fifth-year graduate student working with Mercedes Lopez Morales. And prior to joining the CfA, Chani completed her undergraduate at the University of Montana. And Chani's research mainly focuses on disentangling stellar signals from planetary signals in radial velocity data. And the title of her talk today is K2-79b and K2-222b, two small planets with orbital periods beyond 10 days, and a new method for disentangling planet and stellar signals. So please take it away, Chani.
All right, thank you, James. So yes, I'm talking about two stellar systems today, K2-79 and K2-222. That is hard to say. And I just wanted to first provide you all with a short table here, just kind of summarizing some of these parameters. As you see, these are very similar to our sun. One's a little bit, or I guess they're both a little bit larger, and then one's a little bit more massive, one a little less. But G-type stars, and they both host these small transiting exoplanets that were detected with K2. And as it turns out, we've actually had this HARPS North data for these two targets for quite a while now, but the data was not looking like the most fun to work with. And I can tell you from experience that it's fun, but it's also not fun to work with. So some of the reasons for that is that we saw this early on in the light curves, saw this evidence of potential stellar interference right at the orbital period of the planet. And this is true for both cases, both K2-79 and K2-222. And some of this evidence is if we look at the P-Rho max values that we have estimated with it was SPC that provides those, the stellar parameter classification tool, we can actually calculate an affiliated P-Rho max, and we get this 23.8 and 17.5. And we know that because these planets transit, it's going to be within a couple days of those values, the rotation period. The inclination is reliably somewhere near 90 degrees. And so the problem is that the period of K2-79b is going to fall right near the first harmonic of its P-Rho max measurement. And then K2-22b falls right actually at P-Rho max itself. And as I said, the K2 light curves, when we remove the transits, both in periodogram analyses and ACF, gave us some cause for concern that we may be seeing signals at the orbital period of the planet. So the problem is that when we see stellar signals that just have almost the same exact periodicity as the planet we're looking for, it really impedes our ability to accurately measure a mass if they're overlapping, or it can anyway, depending on how those two signals are interacting and what their respective phases are. So what I've proposed is to instead use, or I guess not instead, but to use these seasonal analyses of the HARPS North RVs, which I think is something that's been done quite a bit, but then also to do this in the activity indicators so that we can really try to identify if one season over another, because we have two seasons for both of these targets, is showing less interference at the orbital period of the planet from the star. And so, and really this comes down to an issue not of precision, but of whether we are confident in the actual accuracy of the number we're achieving. So moving down here, these are some RV periodograms that I've calculated for the two targets. We have K2-79 on the left and K2-222 on the right. And just, there's a lot to look at here. So what you're looking at is in the top row, we see the RV periodogram. In the dark purple, we have all of the RVs. In the cyan color, we have just the season 1 RVs. And in magenta, we have season 2 RVs alone. And then as you step down through these panels, everything below the RV is going to be an activity indicator. So these are various indicators that we track in the spectra that are going to give us some idea of what's going on with the star, and if some of these periodic signals can be attributed to the star and not in fact the planet. So this blue dotted line here is the period of the planet, 10.99 days, the known transiting planet. And as we move down, I just want you to start at the top and just focus on that blue line and move all the way down. what you're going to see is that consistently we see peaks, maybe not necessarily statistically significant, but peaks in the second season that we don't see in the first season. So in the magenta that we don't see in the blue. And here in particular, we see this peak in the bisector inverse span that is a statistically significant peak right at that orbital period of that planet. And so the question is, this peak that we're seeing in the RVs, is this really something that we can attribute all to the planet, or is this interference from stellar activity at that period going to get in our way? And one thing to notice is that season 1 looks like it's quite promising, because we do see a peak in season 1. And I apologize, this is harder to see than I thought it would be, but right here we have our season 1 peak. But as we move down the cyan lines, we don't see any peaks really in the activity indicators. So that's a good indication that maybe season 1 is going to be a better estimate of this semi-amplitude. And we see the same thing going on here with K2-222. So as we move down the period of the planet, the orbital period, we see peaks in season 2 that we just don't see in season 1. And this one's slightly less concerning because we don't see any statistically significant peaks in the activity indicators. But one thing that I do want to mention, and that you may see here, is I'm tracking 10% false alarm probability instead of 1%. And this is in big part due to the fact that these data sets have fairly large error bars, and they also have had sampling that was not, the cadence is not particularly high, and it was not optimized for stellar activity. So there's a lot of things that are kind of working against us here in terms of trying to characterize the stellar activity. So just summarizing, activity indicators in both of these stars are showing this potential for interference at the period of the known planets. But in season 2, we see that interference more, where in season 1, we're seeing very minimal interference. And so we think maybe season 1 is going to provide, or is a good check at least, with the full periodogram, or excuse me, full fit, to make sure that we're getting a reliable estimate. So for both of these targets, we're going to perform fits not just to the full RV set, but also to subsets of each of the seasons. And comparing the semi-amplitudes that comes out of this will help us to understand whether that full fit is really suffering from what's going on in season 2. And so here I show you the RV curves that come out of the HARPS North data for these 2 planets. And for K2-79b here, I have listed the semi-amplitudes that come out of each of the 3. So when we use all of the RVs, and the season 1 RVs, we're seeing this like right around 3 meter per second semi-amplitude. But as you see in the season 2 RVs, we definitely, while they do all agree because of the relatively large error bars on the measurements themselves, the season 2 definitely has converged onto a smaller median value for that semi-amplitude. And I suspect that has to do with what we were seeing up here in the bisector inverse span, where some of what belongs to the planet is actually maybe getting attributed to the star, or missed, or maybe we're seeing some sort of destructive interference going on. Yeah.
Why was the average of season 1 and season 2 so much closer to season 1's value when they both seem to be roughly equal accuracy?
So I think that comes down to what I'm talking about with the potential interference with these. So that's what I was talking about, where it's not an issue of precision, it is an issue of accuracy, because what you're saying is true, that all of these have similar, or at least between season 1 and season 2, we have similar precision. But the thing is that in season 2, what I suspect is happening is that we have this signal that we can see in this activity indicator right at the orbital period of the planet. And I suspect that their phases are lined up in a way such that we're seeing some destructive interference happening there at 11 days. And so in season 2, if that destructive interference is happening, when we fit the semi-amplitude, it's going to come up looking like something smaller than it actually is. And my concern was, we see that happening in season 2. My concern was if we ran it on all the RVs and we also saw that it was getting squished like season 2, because that would mean that whatever was going on in season 2 with that destructive interference was affecting our whole fit. So does that make sense, Erwin?
Sort of.
Yeah. So really the big kicker is like seeing this signal at 11 days in the activity indicator, because we know this can't possibly be from the planet. It has to be from the star. And so we have to ask ourselves in the actual RVs, how much of the signal, the peak we're seeing in the full RVs, can we attribute that to the star rather than the planet? It creates this degeneracy that's quite tricky. And I think that's why people have avoided these data sets for so long. Ian?
Hi, Chani. Sorry, I just had just a dumb terminology question. You mentioned a inverse bisector span. I was wondering what that means exactly.
Yeah, so the bisector inverse span is a measurement that comes out from the spectral lines. And basically different types of stellar activity, magnetic activity, they're going to cause the shape of the lines to shift slightly. And so it takes the centroid of your line, which would normally be straight up, and it curves it like this. And so the bisector inverse span is literally, if you have this curve, it's like this length right here. But it's just a way, it's just a measurement that we have that can help us to classify what's going on with the stellar activity. And it comes from the spectrum.
Okay, thanks, appreciate it.
You're welcome. All right, so yes, so here we have the curves, and and what I was going to say is, so now looking at K222 and comparing the semi-amplitudes that come from the full fit, the season 1 fit, and the season 2 fit, I feel much better about this one because we're seeing agreement pretty much with all 3 of these. We're not seeing one that's getting significantly squished. And that's also consistent with what we saw in the periodograms, because here we see this whopping statistically significant peak in an activity indicator that also shows correlation with the RVs. So that's good indication that that stellar activity was dominating in season 2. But here we really don't see, we do see some peaks going on in season 2, but they're not nearly as statistically significant. And that shows in our fits where we're not seeing season 2 suffer nearly as much from any sort of stellar activity. So when I see the agreement here between the full RVs and season 1, where we saw very minimal interference at the period of the planet, that gives me confidence that this fit is not being, the K value that we're getting in the end isn't being like dampened or just negatively impacted in any way. And the same thing over here, and this is even better because all 3 seasons agree. Excuse me, the 2 seasons and the full fit agree. Okay, so now getting down to the actual science of what these planets look like. And one more plug I just wanted to make is to say that I just wanted to tell you, so the median error, I was actually curious about this for myself, just looked it up again because I'd seen this before, for on these K2-79 RVs is 4.55 meters per second. So that was kind of a rough data set because we're looking for a 3 meter per second signal in 4.5 meter per second. And same thing over here. Luckily, the 2 meter per second signal, these only had an error of 2 meter per second. So that was a little easier to work with, and we can see this in the data. For whatever reason, these ones suffered a little more. I think that one's the less bright of the 2 stars. Pretty sure these are both photon limited. Okay. And so now just getting down to what these planets actually look like. We've talked about the orbital periods, and these planets at longer orbital periods are very valuable for us to look at because as we step out to longer orbital periods, we can start to understand how the irradiation that these planets are receiving from their stars relates to some of the things that are going on with formation and evolution. And let's see, we've got a big 10.3 mass one, so that's the guy up here. And then we've got a smaller planet down here. And these planets are interesting because one is sitting up here in something called the sub-Saturnian desert, where kind of centered around 3.5 meters per second here, we just see this steep drop off in planet occurrence. And so it's interesting because we see it in this place population where we just don't necessarily see that many planets. And this other guy, the smaller one, he's interesting because, I guess he's a he, because it sits at this area actually that's just straddling the radius gap. So it's harder to see in the mass radius representation, but if we plotted this in radius radiation space, you'd see it a lot clearer. But right here, as many of us know, there's this existing radius gap. And this one sits right at the edge of that. So, and then something else that's really interesting about these planets is that we actually see a possible second exoplanet signal in the K2-222 RVs with a period of about 150 days. And this signal is just whopping. So please read the paper when it comes out if you're curious about that. But my inclination is to believe that this is a planet, but I think it's better to also always be a skeptic. So And we have some phase gaps in there. So I'm really going to push to keep observing this K2-222. And another thing that I mentioned is now that we have mass and radius measurements for these, we can kind of start to get a feel for bulk density. And so we can place these in mass, radius, irradiation space and start to get to a feel for whether they support water rich or water poor formation. Because this has been a big question for a while, is with these small exoplanets, as they get to large enough masses, are they just rocks that are taking on like a large amount of HE gas, or is there some water that's getting involved in this? And so there's this wonderful paper from Li Zhang in, I guess, two of them, 2018 and 2019, where he really talks about this in detail. But an interesting thing about this guy in particular, K2-79, wait, that's the bigger one. Yeah. K2-79 is that it sits in this area where we wouldn't we wouldn't at all, based on simulations, expect it to retain a hydrogen helium envelope based on the high level of irradiation it's receiving, which is it's over 100 times the irradiation that Earth receives. And so it's really, this one in particular is really favoring this water rich formation, and it is probably evidence that there is something going on there with some heavier elements. So please check in with the paper with that too. I wanted to focus more on the methodology here, just because I think this is something that can be applied to many data sets, looking at the seasonal behavior of these activity indicators. And particularly when we see these very difficult situations where the star is giving us a periodic signal right at the period of the planet, I think it's important to try to identify seasons where we're seeing minimal interference. With that, I think I'll open it up to questions if anyone has any. And yeah, I think I covered everything I wanted to say.
Thanks, Chani.
Thank you.
Really good work. So do we have any questions? Chima, straight in. Go ahead.
Oh,
please.
look at you.
Yeah, so this is awesome. So I'm just wanted to just like clarify the methodology here. So what happened is you had the transit of the planet, you subtracted that out from the RV signal, and then you use the remaining RV signal to see where the peaks arose in the periodogram, which signified that that was stellar signal contaminating your data. And then you use whichever two had the least amount of stellar contamination, correct?
Exactly. Yeah. Yes. There was one thing at the very beginning. There's two periodograms that came into play here. So the early evidence that we had some stellar signal near the orbital periods of these planets came from the light curves, the transit removed light curves that you mentioned. And so that's actually why for a long time these RVs just sat there and people just kind of passed them up for data sets that looked a little more promising, or maybe just not quite as tricky. So yeah, when I got this data set, this is actually what was really exciting about it to me, is I had this idea for a while about looking at these seasonal analyses and in the periodogram, trying to identify where we're seeing the minimal interference. So that was why the data got put on the shelf for a while. And then I came in and then looked at these RV periodograms to try to get a better feel in these activity indicators that we have available for what's going on season to season.
So you don't do any like stellar correction or anything to when you're analyzing the RV data. You just use like the data that has the least amount of stellar contamination from that season.
So I actually no, good question. I've actually done both. So I'm running fits on the full data set and then season 1 and season 2 individually. I ended up using the full data set as the final fit because it showed that we weren't seeing this negative interference from season 2. But had we seen something where that was getting really damped, maybe a fit to season 1, even though it's fewer points, would have been better.
Okay.
Yeah. Oh, and then as far as fitting for stellar activity, I actually did run a bunch of these fits both with and without GPs, Gaussian processes. And the Gaussian processes, they did better on the season 1 data alone than with anything else, I suspect, because the stellar activity isn't interfering right at the orbital period of the planet. But as I mentioned before, this data was not taken like with optimization for stellar activity in mind. And so the fit definitely struggled with that. And only a couple of the RV or of the Gaussian process fit actually converged.
I have a follow-up. Oh, Victoria, you go ahead.
I was gonna ask about that point of you mentioning that the observations were not optimized for stellar activity. What do you wish had been different? What about the observations would have made it more optimal?
Yeah, you know, I should have put the RVs in here so that y'all could see the gaps, but there's just, so ideally for stellar activity, when we're really trying to disentangle the two signals, you would observe like, it was Xavier Demusk actually wrote a really good paper about this, but like 3 times in a night with like at least half-hour spacing between the observations. But, you know, even that's best case scenario. 2 observations would be great. 1 per night would be great. We didn't even have that. We had like, you know, maybe a couple nights we'll take an observation and then a gap and then like a couple. And so that makes it really, really hard to characterize what the star is doing, particularly because the GPs depend so much on kind of the distance between respective points is what's going to define how correlated they are. So it really just makes it much trickier for the model.
So also on that point then, if one of these seasons for both planets is not done in an optimal way to characterize a stellar activity, does that mean that season might have some stellar activity contamination that you're just insensitive to?
Definitely. Yeah, this is
Right.
this is something worth mentioning. And this is where, where, you know, these final RVs that we end up with, I'm telling you that this is the way I'm interpreting it, but there's really no way to know, like maybe both of these seasons are being horribly impacted by stellar activity. And we just can't tell because, as you're saying, like we didn't observe in a way that we're able to even characterize it in the periodograms. So what I would say is that this is the best that we can do for now with a data set of this quality. But I do think that, especially in the case of like one like K2-222, where we're seeing that this may be just a more interesting target overall because of where it's sitting in mass radius space, and then also with the potential second planet, I really do think it'd be great to go back and do a very optimized strategy for observing this target.
Yeah, that's interesting. Thanks.
You bet.
Any more questions? If not, I have one more. I was wondering, can you place any meaningful constraints on the semi-amplitude of the planet based on mass radius relations? Or would those constraints on the semi-amplitude be so imprecise as to be not useful?
I think it's hard because it's so dependent on composition, right,
Mm-hmm.
of the small planet. And our mass radius, all of the mass radius relations that we have are not, they have a fair amount of uncertainty associated with them. So I don't think you would necessarily do better than the MCMC already does itself. Yeah, and I just place like a Jeffreys prior somewhere between 0 and 10 on it. That's one of the few parameters that I just really let walk and don't try to start it in a super smart place because you just don't know. But that being said, Jason Eastman, who wrote ExoFast, which I should mention I'm using for many of these fits, as well as Raidvel, he, oh, what was I going to say? Dang it. Oh, I just had a brain. Can you remind me what your question was?
I was asking about whether you can place meaningful constraints on the semi-amplitude.
Yeah, that's what I was going to say is he does when, like, if you run, for example, a transit fit, he does give you like an estimate of the semi-amplitude for your RV fit as well. But it's got a pretty large error bar because of that uncertainty due to composition. Yeah.
Interesting. Thank you.
You're welcome.
Okay. Any last questions? Nope. Okay, then. Thank you very much, Chani.
Thank you.
Really great talk. And we can move on to our second speaker today.
All right. So our second speaker today is Bouma. Luke is a finishing graduate student at MIT, working on exoplanet and stellar astrophysics, and he'll be starting in the fall as a 51 Peg Fellow at Caltech. And today he's going to tell us about a hot Jupiter in the halo of a young open cluster. So go ahead, Luke.
Great, thank you, Sam. So a couple things. One thing is I'm a finishing student at Princeton. I did start my grad studies.
Oh, geez, I said MIT, sorry, yes.
All good. I started my graduate studies at MIT, but transferred, and I've been finishing them at Princeton. So that's one thing. Another thing is, so for this title that I've given, a hot Jupiter in the halo of a young open cluster, I realized after pinning down the title that it's a little imprecise. A more precise title here would be a hot Jupiter and the halo of a young open cluster. And I'll hopefully make it clear why that word change is important, because the hot Jupiter that I'd like to talk about today, TOI 1937ab, is potentially a young hot Jupiter. If not, it's definitely a tidally spun up hot Jupiter, but its association with basically the outskirts of a young open cluster is still something that I've been digging into, and I don't have a firm conclusion on it yet. So hopefully I'll go through the various steps and it'll become clear what the situation is. I'd like to start though with some broader context for why, generally speaking, we are interested in finding and exploring young planets, especially young planets that transit. So the main reason is that when we think about processes in planetary evolution, they happen relatively quickly compared to the ages of most planets that we know about. Most planets that we know about orbit field stars, which are typically billions of years old, but the time scales for planet formation are much shorter. They're millions of years old. So if you want to know, for example, how the different archetypes of planetary systems form, how the hot Jupiters form, how the mini Neptunes, the super Earths, then you have to dial back the clock, and looking at young planets is a way of doing that. So to give you an idea for the processes and the aspects of planet formation and evolution that are most important for this work, I've sketched out a couple on this timeline here. And for gas giants, which are the focus of this work, they form when the gas disk is still around, so within a few million years. Rocky planets can take somewhat longer to build up their mass through collisions afterward. But for gas giants, after they form, they're still hot, they're bloated, and they contract just through thermal cooling, Kelvin-Helmholtz cooling. And some of them, depending on the details of their masses and also of the radiation environment, are going to have atmospheric outflows, which have been observed, for example, in lines like Lyman alpha, H alpha, recently metastable helium, as well as folks here are probably aware. And so that kind of gives an idea for the type of evolution of the planetary interiors and atmospheres. But then there's also evolution that can happen of planetary orbits. And that kind of orbital evolution, dynamical evolution, can be really important for understanding, say, the hot Jupiter population, which is really one of the earliest questions that we have in exoplanet science. How do the hot Jupiters form so close to their host stars? Do they form in situ? Seems unlikely because the gas and the dust is so hot and rarefied close to the star. So if they form far away, when they migrate, do they do that early on through coupling with the disk itself? Or might they do that later through a set of processes that I'll call high eccentricity migration, which generally the idea here is that there's some process that excites a highly eccentric orbit for the giant planet, say planet-planet scattering is one of them. And then once the orbit is eccentric enough, you can circularize it through tidal interactions between the star and the planet, which are strongest at the apoapse of the eccentric orbit. So one way to tell the difference between these two scenarios is to look at very young stars and to search them for hot Jupiters. And it's a little bit of a challenging problem because young stars are rare. And so you need to, since hot Jupiters are also rare, you have a doubly rare problem, right? Hot Jupiters, you have maybe 1 in 100 stars, and then only 1 in 10 transit. So you need to be looking at tens of thousands of stars that are young. And right now, if you look at the data, if you ask the NASA Exoplanet Archive, sorry, what was that?
Okay, I don't have my hearing aids on, so I can't hear you well, but.
Good. So if you look at the data from the NASA Exoplanet Archive, then what you see is that there really aren't that many young hot Jupiters that we know about, even though hot Jupiters generally have been known about for a very long time. Here I'm highlighting the planets younger than 100 million years. And you might also note when I'm showing these data, the points don't have error bars on the age axis. And the reason for that is that most of these ages, like I sort of alluded to, aren't very precisely known. So that's because most of these planets orbit field stars. And for field stars, we only get isochrone ages, which, because stars don't move much on the main sequence, aren't very constraining. The exception really for precise ages comes from planets in open clusters and in moving groups. So these planets that orbit stars in coeval stellar populations can have precise ages through their stars. And those ages come from ensemble isochrone dating. So, for example, you have an open cluster with the main sequence turnoff, or potentially you have, M dwarfs that are still contracting to the main sequence. And then there are a set of other age dating techniques that we can use as well. But so overall, the situation is that now basically from K2 and now TESS, people are finding planets around very young stars. And for the most part, they're somewhere in, I think, what has been referred to in this call as the Saturnian desert or something like that. They're in a space where usually we don't see that many planets around the field stars. They're between 5 and 10 Earth radii. And V1298 Tau, for example, is a great example of a system that has 4 large giant planets that are sort of abnormally sized. In general, though, it would be good if we could study planet occurrence through time, in particular for hot Jupiters, in order to get at this question of how do they form. And so in order to do that, I've been looking through the TESS data for transiting close-in giant planets. So I started a project a while ago called CDIPS, the Cluster Difference Imaging Photometric Survey. And the idea of this project is that we know a lot about young stars now from Gaia. And so we search the TESS images. We take the images, we make light curves from them, and we search them for planets around young stars. And one community TESS object of interest that I found through this process was called, I think, K2-79b number. It was fortunately promoted to be a TESS object of interest so that we got a shorter number, which is very helpful. And I originally reported it to ExoFOP because I thought it was in the halo of NGC 2516, based on results from a group that had done a clustering study on the Gaia data to figure out where the young stars are. But I didn't really know what this meant. And so I've actually been going on a deep dive into open cluster evolution a little bit in order to understand what this means. So I'll tell you a little bit about the open cluster first, and then the planet second. So here on the top left here is, or are 3 panels that give us an idea for what you get from the Gaia data. So what's done on the Gaia data now there are a couple different groups around the world that are doing this, is they take the positional data, the right ascension, the declination, the parallaxes, and also the proper motions. So only 5-dimensional Gaia data, they ignore the radial velocities because they're pretty sparse. And then they cluster. They run machine learning algorithms on this 5-dimensional data set in order to identify clumps. And what the algorithm gives you for this particular cluster, NGC 2516, is a large sort of central overdensity and a diffuse population around it. And this isn't the only open cluster that shows this kind of diffuse halo type structure. There are now at least a few dozen within the nearest kiloparsec of the sun that have these kinds of halos. And if you're looking to sort of learn more about this, I'll refer you to Stefan Meingast's recent paper. He calls the halos coronae. I prefer halo, but regardless, the structures are pretty interesting. If you look at them top down inside of the Milky Way, so that the galactic center is over here, the sun in this diagram on the far left would be roughly where my mouse is up here. Then they're elongated mostly inside of the plane of the galaxy. So they're also not at all spherical, right? Their axis ratios are something like 20:1, which is maybe different from what you might expect. It's not what I learned about open clusters being in my intro to astronomy class. I was told that open clusters are supposed to be tens of parsecs in size and spherical. This is hundreds of parsecs in size and very elongated. So I don't know about you, but and then the important detail, of course, my planet candidate at the time is way on the outskirts of one of these arms of this halo. And so I was worried, right? Because I had no idea whether this halo was real, for one, or whether it was just some sort of artifact of a machine learning algorithm. And so I really needed to dig into it a little more. And fortunately, the test data actually let us do this now, because we can measure rotation periods from test light curves, and rotation periods tell us about stellar ages through the gyrochronology concept. I'll mention those in a second. Of course, we can also, the simpler thing to do is when you look at the isochrone data or the HR diagram from Gaia, which it roughly supports the coevality of the core and the halo, and that the halo stars have the same main sequence turnoff as the core. But the rotation, in my eyes, was what really solidified the existence of the halo as a concept. So what I did is I took these light curves that I made, and I measured rotation periods for a couple thousand stars. And what they show is that for the F dwarfs down through about the very late K dwarfs, or it's actually mid K dwarfs when the dispersion starts increasing, there's this nice slow sequence, is what the gyrochronology literature calls this. And this sort of thing has been known about for a long time. It's been discussed in work by like Sidney Barnes, Soren Maibaum published a lot of papers on this topic. And the general thought is that stars are magnetically braking due to their winds carrying away angular momentum and being trapped in the magnetic field of the star, and then the star feels the back reaction. There are, of course, some exceptions to this magnetic braking rule. There's a fast rotating sequence, which has been observed in other similar young open clusters like the Pleiades. And we do get into all of that. And actually this dispersion that we see for the later stars is real as well. That's not measurement error. But regardless, as far as the overall plausibility of the halo as a structure, what we can do is we cross-match our test-derived rotation periods with the Gaia positions of the stars. And here in these bottom three panels, I'm showing the stars that should have shown rotation but didn't in orange, and the stars that did show rotation, and they're shown up in these diagrams in blue. And for the most part, the stars that we expected to show rotation, which should have been all of them, do span the entire size of the halo, which I didn't know really what to expect here, but it was a sort of a helpful piece of evidence in support of the youth of this planet A, and independently for the fact that these structures exist and that we can find them now with Gaia. I think maybe the latter is, I think, of somewhat broader significance than this one planet, because thinking generally about the search for young planets, currently, like I mentioned, we're limited by the amount of young stars that we know. And so the fact that the mass content of these open clusters is significantly spread out in a way that we can now identify will, I think, be helpful for future projects. I'll also just briefly mention that we looked at the lithium content of the stars as well using ground-based spectroscopy. This is another youth indicator that we can have. And generally speaking, they all support the same story, that the halo is younger than field stars and has a consistent age as the core. So let me go ahead now and talk a little bit about the planet. It's actually, it's a bit of a tangent, but the lithium shows interesting correlations with the stellar properties too. So for example, as a function of stellar color, the hottest stars are lithium depleted relative to the cooler stars, the K dwarfs. And then they become more depleted again for the M dwarfs. So the M dwarf depletion is understood through the lithium burning in the stellar core, because their convective zones are deeper. And so it's transported all the way down. For the hottest stars, it's the opposite. The convective zones are very, very shallow, but they're hot enough that this particular line, since it's a resonance line, has its ground state fully excited. So it's only ions in the atmosphere, and we can't get the ground state to the doubly excited state transition that we would otherwise need to see this line. So for the K dwarfs, where we see it most often, there is some interesting correlation with the rotation period, which is probably tied to processes inside the star. But anyway, know thy star, know thy planet. The planet, going ahead to that, is, well, the main evidence that led to its discovery is shown in the top left here. This is from the test data. It's a preliminary fit, which is why the residuals here are large. I've really been focusing on the cluster for the time being. That's the first in a series of 2 papers. But the reason that I'm pretty confident saying that it's a planet isn't from the test data, because as many of us are aware, the test data can come with many false positives. The pixels are large, so we need to worry about eclipsing binary contaminants, especially for giant planets. But what we did for this particular case was we got a dozen radial velocity measurements from PFS at Magellan, and the RV curve here, which is also preliminary quick fit, basically can only be interpreted as a hot Jupiter with a slightly super Jovian mass. And we have some other supporting ground-based observations as well from the Las Cumbres Observatory Global Telescope and multicolor photometry. It's all good. We also have a Rossler-McLaughlin measurement that shows the planet is on an aligned orbit with its star, which makes sense because the star is a G dwarf. I should mention it's spectral type G2V, so basically sun-like. And so it's cool enough that, given the correlations that have been observed for the hot Jupiter population, we wouldn't expect it to be on a misaligned orbit. So the planet's real, which is always good. Is it interesting? Well, I think probably the most uncontrovertible surprising thing about it is shown in this middle panel here. So here I'm showing you for known hot Jupiters that have measured stellar spin periods, mostly photometric, a few from very precise V-sin-Is. I'm showing you their spin periods against the planet orbital periods. And the sort of surprising thing about TOI 1937 is that it lives in the bottom left of this parameter space. So the host star, like I said, it's sun-like, right? So if it were solar age and there were no tidal interactions between the planet and the star, it would have a spin period of 21 days. And it's a factor of 3 smaller than that. So in addition, it's also on a short orbital period, which there are very few hot Jupiters for which they have sub-day orbital periods. So the implication there is that the spin period of the star, even if the age isn't actually young, even if it's a field star that's a gigayear, is telling us probably something then about tidal evolution inside of the system. Because we expect at a population level that hot Jupiters are tidally unstable. They should be inspiraling over timescales that aren't entirely certain into their host stars, but they probably merge with their host stars while the star is still in the main sequence. So this system could be an example of that process underway. With respect to the youth overall, though, my main source of concern about it is shown in the top right. So these are those lithium measurements I was mentioning for the cluster, which come from a survey called Gaia ESO and also an Australian survey called GALA. And most of the stars in the cluster, like I mentioned, are elevated relative to field stars, shown in gray, in their lithium content. I should mention I'm showing lithium equivalent widths here, but they transfer over to the abundance of lithium in the star as well, which is the physically meaningful quantity. Our preferred target here has the lithium content of a field star. And as far as its youth, I think if we were going to have a report card where it was doing okay in kinematics, it was doing okay in rotation, in lithium 101, it fails. And so it's not necessarily a nail in its coffin, but it's certainly worrisome. And you would have to basically invoke an and then process, a tooth fairy, in order to explain it. You would need to say something like, oh, well, maybe the rotation of the star or the presence of the hot Jupiter affects the lithium content, which is totally post hoc reasoning. So hence my worry. There are a couple other youth indicators that you could consider, like, does the metallicity of the target star match that of the cluster? Sure, more or less, but metallicity measurements from spectra are difficult to make precise. This one, the rotation period and the orbital period of the hot Jupiter, using that as an age indicator, I think is not particularly kosher. It's not been done very much, and it's an indirect argument, I think. So I think overall, the situation on whether or not the star is truly young, if it is, it would be, I should remind you, something like 14 Earth radii, 150 million years. It would be basically the youngest, I think, definitive hot Jupiter known. Qatar-4, which is this point here, is, I see Dave is on the call, probably not this young. This age is based on a gyrochronology measurement, which for the young stars are a little bit, or not for young stars, gyrochronology age measurements for hot Jupiter systems are a little bit questionable, because the star and the planet are thought to tidally interact, which can spin up the star. And so, that can produce an anomalously young age. I think definitively right now, the youngest hot Jupiter that I'm 100% sure exists is Kelt 9, which is it's a hot Jupiter around an A star. And so the star's age is known because it's close to the main sequence and it doesn't evolve it should evolve quickly, but it hasn't. So let me just make a few concluding remarks. So one of the things that I learned from looking into this study was that the age dimension, in my eyes, really has yet to meaningfully constrain hot Jupiter arrival times, in the sense of, does the youngest hot Jupiter known right now tell us that it needed to have formed through disk migration versus through a high eccentricity migration pathway? I do think, though, that TESS is observing enough young stars to be able to change this. For instance, there was a candidate, very young hot Jupiter, 10 million years old, called PTFO 8-8695, that we were able to show with TESS is actually a false positive. There's also a candidate hot Jupiter right now from Aaron Rizzuto and collaborators that we're trying to measure the mass of right now. This is a 10 million year old system that has been called a hot Jupiter, but there are reasons that I'd be happy to discuss to sort of question whether its mass is Jovian or whether its mass is Neptunian. But overall, I think right now we're in a regime where we just need detections before we can do statistics. And one path toward getting detections will be expanding our knowledge of young stars generally. And the fact that Gaia is finding these halos around nearby young open clusters will, I think, really help us, because the clusters have lots of stars. It's a factor of 2 or 3 increase in our sort of census of the young stellar population. For this one particular halo, I've been able to show with the test data and also ground-based spectra that the halo is real, which I wasn't sure about whether I expected. I tend to be skeptical of machine learning algorithms, and in this case, it actually was right. It taught us something. So, that's a point for the machine learners. For this particular hot Jupiter system, I've made the case that it's definitely tidally spun up, and it might be young, but there are some additional work that might be needed, either in precision spectroscopy, maybe in studying its M-dwarf companion that I haven't really mentioned at all. It's a binary system. The M-dwarf might still be contracting. And overall, I think the situation is one in which just a broader analysis of the test data will be the most useful thing in the future. Thanks for your attention. I'd be happy to take any questions.
All right, do we have any questions? If you have a question, you can raise your hand in the chat. Yes, Sean.
Yes, I have a question. Good talk, Luke. So I was wondering, could you just talk again about the lithium abundance connection and why the low lithium abundance suggests that this is, well, why that would give an F for the young score? I remember that correlation plot, but if you could just cover that one more time.
Absolutely. So the general idea for G dwarfs, at least, is that the lithium depletion should happen over very long timescales of hundreds of millions, billions of years. So, in the sun, for example, we see that relative to the primordial lithium abundance that's seen in like the interstellar medium, it's like a factor of like, I think 200 depleted or something like that. But young stars, that depletion hasn't happened yet for the G dwarf. It might be a factor of a few depleted, not hundreds. This particular star, TOI 1937, is a factor of like 100 depleted.
Okay, gotcha. Makes sense. Thanks.
So, chime in.
Hi, yeah, so good talk. And I was curious about the fact that you said that like 33% of the stars you couldn't measure the rotational period from photometry. And you said that's like a surprise. Why is that a surprise? Couldn't that be the case just because it'd be harder to measure the period when the star is less active?
So as far as we know, basically all young stars should show a rotation modulation, subject to the spectral type and stuff like that. All sun-like young stars should. For example, from work with the Kepler telescope and K2, the typical fractions with those longer and more precise data sets are more like 90%.
Mhm.
So I think what we're seeing, from only 2/3 showing rotational modulation is probably a mix of field star contamination, probably explaining, I don't know, 25% of it. Then maybe the remaining 10% is from the same sort of stuff that affects the rotation period detection in the K2 data. So, which is like, for example, if the star is pole on, then you might not see the star spot on an equator. But that's I think a relatively small fraction. I think probably our initial kinematic membership from Gaia, that list was probably contaminated.
Okay, I see. So it's surprising because we're assuming initially that they're all cluster stars, but in fact, that's likely not the case. I see.
Exactly. Yeah. I mean, I don't think people might have different intuitions for the efficacy of machine learning algorithms, but for the work that's been done clustering on the Gaia data, at this point, there hasn't been that much effort to quantify the contamination rates from field stars. And when you use different algorithms, you get different results. So in selecting my initial member list, I tried to be as unrestrictive as possible to get as many true positives as possible. But that means I also let in a lot of field star contaminants.
Right. Okay, that makes sense. Cool, thanks.
All right.
Yeah, I'll be quick. Thanks for the talk, Luke. So you have pretty much convinced me that it's tricky to call this a verified Young system. But so do you have the measurements and tools available to you to attempt a application of gyrochronology to the system? So you mentioned that you do see rotation in TOI 1937, correct me if I'm wrong. And I guess I'm just curious, if you did apply that, what sort of range of age values you get based off the color, rotation period, etc.
Yeah, so yeah, we do have the rotation period, and I can just show it really quickly on my screen here. It's a little bit slower than most of the stars in the cluster, which take from that what you will. In terms of, should we apply this to derive a gyrochronological age? So if you did, then you would get an age between Pleiades, which is basically overlapping with the NGC 2516 sequence, and Persepi, which is 600 million years. It's a little bit longer. So its gyrochronological age is between 100 million and 600 million years. Yes. Whether or not I believe this at all, I do not, because the presence of a hot Jupiter is expected to change the rotational period of the star. And so applying the gyrochronological age dating technique here isn't, I think, a valid thing to do.
Okay, thanks.
Thanks for the question, yeah.
So I had a question. You said that we have yet to place meaningful constraints on hot Jupiter arrival times, but test detections could place those constraints. But if the detections never come, can we make meaningful constraints on hot Jupiters arriving late?
Yeah, so in a scenario where all hot Jupiters form over very long timescales, hundreds of millions of years, giga-years, then we wouldn't expect to see anything at the youngest age end. And in order for that non-detection to be meaningful, basically you would need to have a very careful study that showed, hey, we're sensitive to hot Jupiters. Ideally, we're sensitive to smaller planets even, which I think is possible. But basically that statistical analysis hasn't been done at this point. I am interested in doing it, but it's a long project. It'll take a while.
Thanks. All right, any last questions? I don't see anything, so I'll say thank you to both of our speakers again. And unless anybody has any announcements, we will see you in 2 weeks' time.